Hi everybody, welcome to another video in Precalculus section 3.4 properties of rational functions. So rational function is the ratio of two functions, but in this context we define it is the ratio of two polynomials. So we have p of x over q of x, where p of x and q of x are polynomial, and of course we cannot divide by 0. Right. The domain of the rational function is the set of all real numbers. So we only define this function on real numbers, and the real number such that the denominator is not equal to 0. Once again, we cannot divide by 0. Yeah. So we accept those that make the denominator equal to 0. Right. Let's find the domain of this function. So simply we just let the denominator not equal to 0. So here we have x plus 2 not equal to 0. So x not equal to negative 2 on the number line. We can have anything except for negative 2. So we will have negative infinity to negative 2, negative 2 to infinity. Yeah, anything but negative 2. And I'm going to put a union in between them. Right. Same thing here. I'll let the denominator not equal to 0. And then we just solve for x. Subtract 4 on both sides. And take the square root on both sides. Don't forget that when we take the square root on both sides, there will be a plus or minus. So it's a plus or minus of negative 4. Of course, negative inside the square root is the imaginary I. So x not equal to plus or minus I. Yeah, that negative inside the square root is I. Square root of 4, or that is the same thing as plus or minus 2i. So x is not equal to 2i. Everything else is good. But here we define that to be a set of all real numbers. So all real number is different than every real number is different than this 2i. So because of that, the domain here, by the way, let's just yeah, so the domain here will be all real numbers, because all real numbers are different than complex or the imaginary number. So that's good. Yeah, either the graph or the interval notation. Right. Now let's sketch the graph of 1 over x squared. Now we don't have much about rational function. Of course we do, but this is just a review of Cauchy algebra. But as for now, let's say we don't have anything. Let's just say we don't have anything yet. So the way we sketch the graph is we'll find the points. Of course, when we find a point, we don't want to find 0. Divided by 0 is undefined. So we know that the function is undefined 0. So we choose something else. How about negative 3, negative 2, and negative 1? We're not choosing 0, so 1, 2, and 3. Right. We have 1 over x squared, so 1 over negative 3 squared. Negative 3 squared is 9. Negative 2 squared. Just need to do one of them. Yeah. So that would be 1/4, and then 1, 1, 1/4, and 1 over 9. And of course that is an even function. Alright, so negative 3, negative 1 over 9, negative 2, 1/4, negative 1 is 1. So we look at this graph. Of course, the bigger value for x bigger value for x, the smaller values of y, or on the negative side as well. Yeah, so that is the graph. Right, now we have some features of the graph. Notice that the bigger value of x, the values get closer and closer to 0, and when x gets closer and closer to 0, the function goes to infinity. Right, so with that we define the asymptotes. Definition: let R denote a rational function. If x goes to negative infinity on infinity, the values approach some fixed number L, then we have the line y equal to L is a horizontal asymptote. So when we have horizontal asymptote, the equation is y equal to something. And the equation x equal to something is the vertical asymptote. If x approaches to a number and the values of x goes to infinity, of course when we write like this, we mean of x goes to infinity, or of x goes to negative infinity, or it could be something else. Yeah, or we might have something like there's a vertical asymptote here, it is positive on one side and it is negative on the other side. Potentially we could have that as well. Yeah, but that including in this case. Of course, if we want to be complete, it could be in this case as well. Yeah, so one negative infinity and one positive infinity. Right, horizontal and vertical asymptotes. Now, furthermore, we can have that the graph for as far as the asymptotes go, the graph of the function may intersect the horizontal asymptote, but the graph of the function will never intersect a vertical asymptote, because if we have the vertical asymptote and the function going like this, it cannot be a function, because it's not even a function, it failed the vertical line test. Also, it will not cross it, because the vertical asymptote is where the function is undefined. So that's why it never intersects the asymptotes. Graph of the function never intersect a vertical asymptote, because the function is undefined there. The graph of a function may intersect the horizontal asymptote. Right, next, we define that as x goes to infinity or negative infinity, if the function approaching to a linear function ax plus b, then we have the slant, or an oblique asymptote. So when the function approaching to the a slant asymptote, so this is what we have. Yeah. And if we define rational function being the ratio of two polynomials, then we only have one horizontal asymptote. If we relax that definition, we just say if it is ratio of two functions, then we may have two horizontal asymptotes. Potentially we might have something like this. We have one asymptote on this side and one on the other side. And the function might go like this. Right? So at x go to negative infinity, it goes to a number. At x go to infinity, the function go to another value. So we could have at most two horizontal asymptotes, one for infinity and one for negative infinity. But if we define the function to be a ratio of two polynomials, then it's only one. Unless we have some, if we reduce the definition to ratio of two functions, then we might have two. But if it is between two polynomials, it can only be one. Right. Now, and we find the vertical asymptotes. Well, this is like what we have in trigonometry or the Gaussian algebra. First, the vertical asymptote occurs where the function is undefined. The function is undefined where we let the denominator equal to 0. But at the same time, if the top equal to 0 as well, it is not the vertical asymptote. So we need two things to happen. Bottom equal to 0 and the top is not. The bottom equal to 0, so the function is undefined, and the top not equal to 0, so we will not have, which we define later, is a home. Right, so just find the vertical asymptote for this one. Vertical asymptotes, meaning that the bottom is 0, and then the top is not. So bottom equal to 0, we let x squared minus 4 equal to 0. Move the 4 over, and then take the square root on both sides. Plus or minus square root of 2, or plus or minus 2. So we have x equal to 2 and x equal to negative 2. Yeah, so that is half of it. Now, we do need to check to make sure that the top is not equal to 0. So we have 2 and negative 2. All we do, we just need to check when x equal to 2, what is the top? We're going to put 2 in for x. And that is not equal to 0, which is good. Now, at x equal to negative 2, the top equal to negative 4, which is also not equal to 0. So it's good. Right? So the bottom equal to 0, whatever numbers we have, make sure that the top is not equal to 0. So in which case both of them check. So the vertical asymptote, we have x equal to 2, and x equal to negative 2. Right, so simple enough. The bottom is 0 and the top is not. Right, onto this one. Once again, we let the bottom equal to 0. Bottom equal to 0. We have x squared plus 3 equal to 0. Move the 3 over and take the square root on both sides. And this is imaginary. So if x equal to plus or minus negative inside the square root is imaginary I and square root of 3. And since when we talk about this, remember the asymptotes is to the graph of the function, and the graph of the function is on the real axis, the real values. So if we have a complex number or if we have imaginary number, it's not going to be on the graph because the graph is only for real numbers. So in that case, since in that case this the imaginary doesn't count here, so in this case the bottom cannot equal to 0, therefore we have no vertical asymptote. So we have no vertical asymptote. Because there's no real values that make the bottom equal to 0. Imaginary does not count. Right. Next, same thing here. Bottom equal to 0 and the top is not. X squared minus 5x minus 6 equal to 0. We can factor completeness square, quadratic formula. It doesn't matter. Here I can just factor to get to negative 6, either 2 and 3. Yes, but they should have opposite sign because the product is negative 6. So that should be negative 6 and plus 1. Yeah. When x equal to So in that case we have x minus 6 equal to 0, x plus 1 equal to 0. So we have x equal to 6 and x equal to negative 1. Alright, we have two values that make the bottom equal to 0. Now we just need to show that check that the top is not equal to 0. So when x equal to 6, I'm going to put 6 in for x for the top. 6 square, 6 plus 1, which is 7. Yeah, just check for the top, and that is not equal to 0. So that's good. That is the vertical asymptote, x equal to 6. Now we can just put that. Then, when x equal to negative 1, the top equal to negative 1. For x plus 1 is equal to 0. And of course that doesn't work. We need the bottom not equal to 0. The bottom equal to 0. We need the top not equal to 0. So this doesn't work. So in this case the vertical asymptote is only one of them, x equal to 6. So we need to verify that the bottom equal to 0 and the top not equal to 0. So we need both of them. So let's see, x plus 1, x squared minus 5x minus 6. See the graph. As you see, there's the vertical asymptote at x equal to 6 here. But at negative 1, it did not show at all. So if we try to draw the graph here real quick, if we just show the sketch. So if we graph this, we have a vertical asymptote at 6. And a function going like this. And then so what happened at negative 1? We know for sure that at negative 1 the bottom still equal to 0. So it's undefined, so there will be a hole at negative 1. So that's what we have in the note. Note, if the bottom equal to 0 and top equal to 0, then we will have a hole in the graph. So we will have a hole in the graph. So that is where the function is undefined. But we're just missing one point of the graph. Yeah. The calculator did not show that, but at negative 1 they're missing a point there. Right. Multiplicity and vertical asymptotes. It says that if the multiplicity of any zero of the denominator in the lowest term, if it's odd, one is positive, one negative. If it's even, both of them is positive, but both of them is negative. So here we have 1 over x squared. When x equal to 0, the bottom equal to 0. So x equal to 0 is the vertical asymptote. Multiplicity of 2. So both of them, in this case, point up. Right. So the multiplicity, if it is even, they either both pointing up or both pointing down. If it's negative, one points up, one points down. So that is an odd and even multiplicity of the factor that make the vertical asymptotes. Yeah. Right, so that is the vertical asymptote. Very straightforward. Bottom equal to 0, and the top is not 0. Horizontal asymptote is even easier because there are only a few scenarios. This is very clear. So we will look at, once again, the definition here is for the rational function is the ratio of two polynomials. So since we have the ratio of two polynomials, we will have degree on the top and degree at the bottom. If degree on top is less than degree at the bottom, we have y equal to 0. Simply, if we have something that is too small on the top and the bottom is going too big, think about this. The bigger number we have at the bottom, where the top is constant, then that will go to 0, right? So that's what it is. So when degree on top is less than degree at the bottom, so the top go to the infinity slower than the bottom, could be. So in that case we have y equal to 0. If the top is bigger than the bottom, if we have this reverse, the bigger number we have, the bigger the quotient we have, and therefore we have no vertical asymptote. So when it's less than, is y equal to 0, and when it's greater than, there's no vertical asymptote. Because that always a typo, right? That should be horizontal. Sorry. And when we have the degree equal to, we will have the y equal to the ratio of leading coefficients. Right. On a special case, when we have degree on top is exactly one more than the bottom, that's where we have the slant asymptote. If the quotient is not equal to 0. I mean, if the remainder is not equal to 0, then y equal to quotient is the oblique asymptote or the slant asymptote. So the degree is bigger on the top, will be 0, bigger the bottom, there will be none. If the degrees are equal, then we divide the leading coefficient. And if you look at online, there's the acronym like this: bigger on the bottom, there will be 0. Bigger on the top, there will be none. And if the exponent are the same, then we divide the leading coefficient. Yeah, because you search that online, because that will bring this out. It doesn't make a lot of sense, but that's what they have. So I'm just going to write that out. Right, so that's for the horizontal asymptote of this. So it's very straightforward. All we have to say is, what is the degree on top? It's the highest power of x on the top, which is 2. Degree at the bottom, highest degree of x at the bottom is also 2. So when they're equal, we have the horizontal asymptote is y equal to the ratio of leading coefficient. Leading coefficient, we have 1x squared over 1x squared, so 1 over 1, which is 1. So the horizontal asymptote is y equal to 1. So the scenario is very clear. There's no confusion about this. Right, next, for the next problem, degree on top is equal to 2. Degree at the bottom. Notice that this is the highest degree of x at the bottom, would be 4. So what if we have degree on top is less than degree at the bottom? So bigger degree at the bottom. So y equal to 0 is the horizontal asymptote. So So bigger the bottom, y equal to 0, bigger on the top, there's none. Which what we have here. Degree on top is 3, degree at the bottom is 2. Now degree on top is bigger. So we have no horizontal asymptote. So we have 3 scenarios. When they equal, we divide the leading coefficients. When degree at the bottom is bigger, y equal to 0. When degree on top is bigger, there's no horizontal asymptote. Right. So vertical asymptote and horizontal asymptote, straightforward. The oblique asymptote or the slant asymptote is a little more difficult. So first of all, degree on top is 3, degree at bottom is 2. In this case, no horizontal asymptote. Right, see just right here. So for this problem, there will be no horizontal asymptote because we have degree on top is bigger than degree at the bottom. Simple as that. Next, the oblique asymptote. Oblique asymptote, there will be special case. There will be quite a few things. First, we require to have degree on top is 1 more than the bottom. And the second, the remainder have to be not equal to 0. In that case, then y equal to the quotient is the slant asymptote or the oblique asymptote. Right. So in that case, we have to divide them. For polynomial, we have to use long division. Right, there's no other way around. Long division, we're going to have x squared plus x plus 1 go into this. So x squared plus x plus 1 divide into that. Notice that we have to have the placeholder for there's no x there, right? So we have a placeholder. So we have all the places for everything. Now we just divide. So to divide, we take the biggest degree divided by the biggest highest degree term divided by each other. So 2x cubed divided by x squared, cancel out, we will have 2x. That gives us 2x. Now the 2x multiply back into this. 2x x squared plus x plus 1. So that gives us 2x cubed plus 2x squared plus 2x. 2x cubed plus 2x squared plus 2x. Right. Now we will subtract these two. To subtract, we will change the sign. This positive to negative, positive to negative, positive to negative. And we'll just simply add them. 2x cubed cancel out, 2x squared minus 2x squared is going to be just x squared, right? Yeah, 3 minus 2, x squared. 0 minus, so minus 2x plus 2. Right, now, once again, we divide the highest term, x squared to x squared. Equal to 1 plus 1. and then we multiply it back 1 times x squared, so that we just have x squared plus x plus 1. And now we'll change the sign to positive to negative, positive to negative, and then we add them. That cancel out, so that is negative 3x. 2 minus 1 is 1. And that is the remainder. So the remainder is not equal to 0. Yes, so that is check. By the way, degree on top is 1 more than the bottom, so that also check. So when both of them are checked and y equal to the quotient is the slant asymptote, so in this case the slant asymptote is 2x plus 1. So we have the slant asymptote or the oblique asymptote is y equal to 2x plus 1. Now let's see how the graph will look. First, let's enter this function. I'm sorry, that function. Right, 2x cubed plus 3x squared plus 2. And then over x squared plus x plus 1. And then we have 2x plus 1. Right, let's see the graph. So the first one, we have the graph and the line. So let's zoom out and then do see. Yeah. As you see, it's not very clear. But if the graph like that, when x goes to infinity, this behavior of the function is similar to the line to x plus 1. Yeah. So when x goes to infinity or negative infinity, the function approaching to x plus 1. Approaching to infinity also, but the behavior is like to x plus 1. Now, furthermore, for the ratio of two polynomials, if degree on top is bigger than the bottom, the behavior or the end behavior is the same as we just divide by the highest power terms. So 2x cubed divided by x squared, so that look like 2x. So the end behavior of this is just behave the same as 2x. Right? So it says that the end behavior of the rational function is the same as the ratio of the highest power terms. Right? In this case, just look like 2x. Right? But in this section, I will just go over some basic properties of the rational function, including the asymptotes. Right, I stop the video here. As always, thank you for watching and see you in another video in the calculus.